Here are solutions to homework set number 4 for ECE 461-661. In this homework set, we're looking at review of signals and systems, LaPlace transforms, first and second order approximations. The first problem looks at if you have a transfer function between x and y, what is the differential equation relating the two? So anytime you see s, think differential equation. If I cross multiply, I get a cubic in terms of y. The basic assumption behind LaPlace transforms is everything's in the form of e to the st. So when I differentiate, I get s, e to the st. So s means derivative. So likewise, s cubed becomes the third derivative, second derivative, first derivative, just y, first derivative of x. That's the differential equation that corresponds to that transfer function. Part B is if the input's a sine wave, find y. This is really a phasor problem. This has been true for all time. So if here's t equals 0, there's a sine wave that's been going on for a long time. I know what the answer is. Since it's been on for all time, I know that y of t is in the form of a cosine of 5t plus b sine of 5t. All I don't know is what a and b are. To find them, I use phasors. Do a phasor representation of x. Real part's cosine, minus j is sine. Here's the frequency, 5 radians per second. This is the gain everywhere. All I care about is the gain at 5 radians per second, times the input at 5 radians per second, gives me a complex number. What that means is real part's cosine, minus j is sine. Part C is find the step response. Now this is where LaPlace comes in. At a step response at t equals 0, I kick it. So I have a steady state solution and a transient solution. To find it, I replace x with the LaPlace transform of a step, whenever s. This isn't in my table of LaPlace transforms, so do partial fractions. Then take the inverse LaPlace transform. This is 0.02, 0.25, e to the minus 2t, and so on. And here's my answer. A couple ways to do partial fractions. I can do in MATLAB, input the system along with the step input. So there's the 0. The pole's at -2, -6, -8, and 0. Now evaluate it at the first pole, plus epsilon. I want to avoid 0 because I get 0 over 0 otherwise. So evaluate g of s times s, I get 0.0208. The pole at -2, evaluate at that frequency times s plus 2, gives you 0.25. At -6, at -8. That's one way to do partial fractions. Problem 2. If you have this transfer function, what's the 2% settling time, the percent overshoot, and the steady state output? Well, to do that, I find the dominant pole, that's at -2 plus minus j10, or in polar form, 10.1 at 78 degrees. The settling time is 4 over the real part, 2 seconds. The angle tells you the damping ratio, 0.1961. From the second order approximations, I can convert that to overshoot, 53%. And the DC gain is just when s goes to 0 plus g of s, 1.53. So it tells me here's the step response. I'll have 53% overshoot. Settling time is 2 seconds, and the overshoot is 53%. I can check, throw that in MATLAB, take the step response, evaluate it. The final value is roughly the DC gain. The overshoot is the max relative to DC divided by DC, 52%. And the settling time is how long does it take to get within 2% of the final value. So this is how far you are from the final value in percentages. How long does it keep going? Well, if it's more than 0.02, update t. When I stop updating it, that's the last time I was outside 2%. 1.95 seconds. So there's the actual step response. Here's the 2% settling time. Comparing them. This is the second order approximation. Here's what you actually get using MATLAB. So again, it's not exact, but pretty close. Problem 3 is name that transfer function. Here I've got a first order system. There's no oscillations. So it's in the form of a over s plus b. To get the pole, find the 2% settling time. It's right around here somewhere. I read it as about 0.6 seconds. So 4 over 0.6 is 6.67. That's B. To find A, take the DC gain, so about 2.05. Find A to make the DC gain 2.05. So here's my transfer function. Finally, the last problem. If I'm oscillating, I know I have complex poles and its complex conjugate. So here's the answer. I've got to pull 3 pieces of information off this curve. One is I get the frequency of oscillation. So here's 1 cycle, 2 cycles, 3 cycles. That tells me the complex part of the pole, C. Here's the 2% settling time. That tells me the real part. And the DC gain tells me A. So to get the complex part, I've got 3 cycles and 1.24 seconds. Here's 3 cycles, 1.24. Gives me 15.2 radians per second. That's C. The real part tells me the settling time. About 1.3 second settling time. Yeah, somewhere around here. 4 over that is the real part, 3.08. Pick A to make the DC gain, 2.15. So here's G of S. And that's homework set number 4 for ECE 461.